Okay, we'll get started. Y'all ready? Let's see, we have a leaving group on a tertiary carbon, strong base. What reaction are we doing here? What mechanism? E2. Bimolecular, can't do SN2, on tertiary halide, must be E2. Okay. Did we show 3 possible products last time? We can eliminate beta hydrogen here, put double bond in, carbon-carbon double bond in here, losing the H and the Br. Or we can lose this H and Br, put double bond in here. But that structure would have 2 isomers, E or Z. What are we going to get? Well, you always want to get the most substituted if you can. And if you're doing an SN1, you always get the most substituted or the best product. SN2, you would like to get the most substituted and the most stable if you can, but you have to meet the stereochemical requirement that is listed in bold at the top, which is the leaving group and the H, and we're talking about this H here, because removing that beta hydrogen would give the more substituted alkene, but that H and that Br have to be coplanar with anti-coplanar, highly, highly preferred. Right here is an example of anti-coplanar in a system that can rotate. This has free rotation. We want to get the Br and the H anti-coplanar like that right there. Now, of course, there's going to be other groups on this Newman projection. We need to draw this in a Newman, and we need to rotate it. We can draw it looking here or here. Let's draw it looking down this here. We're looking down this bond right here. If I'm looking through there, looking down that bond, what do I see? Well, first off, circle, circle, dot, dot. Front carbon, what's coming straight down? There's something coming straight down. The T-butyl group, that's a tert-butyl, right? Looking through there, what's coming out towards you off of that carbon? Methyl. Out towards you is to my left. Looking down, out towards you is to my left. As I'm looking down, methyl's to the left. I'll draw that as Me. That's an Me right there. What's on that carbon going to the hull? Bromine. As I'm looking down, the bromine's going to the hull, so that's on my right. Looking down, bromine's going to the right. Looking down, bromine's going to the right. Okay, now let's look to the back carbon. Past the front one to the back. There's something going straight down on the back carbon. Methyl. It's actually eclipsed with the T-butyl. I'm going to draw it straight down, just a little bit to the side. You're going to draw in an Me on it just to make sure we can see it. That's an Me on the end there. It's also an Me there. Well, I drew it there too. Okay, there's an Me there. What's on this back carbon going towards you? Ethyl. Towards you is the left. So I'm going to draw this like that. It's also eclipsed. What's on the back carbon going to the hull? The H. The hull is to my right as I'm looking down. So it's over here. And so there. That H is actually eclipsed with the bromine. It's right behind it. That's one plane right there. But are those anti-coplanar or syn-coplanar? Syn. Yes, they're syn. We want the H not there, but where? I want it right here. In the plane, but anti compared to the carbon. So what we can do is we want to rotate that back carbon. This is the initial view. This molecule is going to rotate. I'm going to rotate it. I'm not going to change the front. The front has a bromine here, methyl here, a T-butyl straight down. I'm going to rotate it and put the H here. And if the H moves here, where's the methyl going? Hold on, what's on the back part? Where's the alpha going to be? Basically, we're rotating the back 180 degrees. Thank you. Where's the alpha going to be? The alpha is going to rotate to here. And what's the other group on the back carbon? The methyl, where's it going to rotate to? Up here. Got one methyl on the front carbon, one methyl on the back carbon. Front carbon, back carbon. Now look at this plane. Now the H and the leaving group, that's a plane right through there. It's a plane of paper. But about the central position, they're anti. Br is this way, the H is this way. Does everybody agree the H and the Br are now anti-coplanar? If you don't, you should agree. The elimination takes place from this conformation. The base takes the H, the electrons move in between the two carbons. We can't see that here. Move in between the two carbons and kick that off. All that's concerted. And when that takes place, the double bond is just put in between the two carbons. You can't see them. But here's the take-home. The T-butyl and the ethyl are on the same side. The two methyls are on the same side. They're not on the same carbon. They're on the same side of the alkene face. So which product is formed? Look at the three. You really only need to look at two. We're making the more substituted one. Of the two, which one is formed? I didn't label them as A or B. I wish I had. Did I? Well, individual compounds. No, it would be the one with the T-butyl and the ethyl on the same side. The product would be ethyl and T-butyl on the same side, methyls on the same side. Okay? That's the product. Now the question we can ask is that the most stable isomer of the two possible isomers? No, the more stable isomer would have the two bigger groups anti. Not cis. But you don't get the two bigger groups anti, because the elimination has to take place through this conformation, and in this conformation the T-butyl and the ethyl are on the same side. Because the stereochemical requirement for elimination is anti-coplanar. Same side, same side. This is how you do these. You have to meet the stereochemical requirement. Questions?
So your leaving group and hydrogen will always be, like, you always want them opposite of each other?
The H and the Br. The leaving group and the beta hydrogen that's being extracted must be coplanar. With anti-coplanar, very much preferred. Right here, they're anti-coplanar. It can eliminate syn-coplanar. This is syn-coplanar. It can eliminate here. And if you did eliminate here, you would get the other isomer. The T-butyl and the methyl are on the same side, and ethyl and methyl are on the same side. But the driving force here is not the thermodynamics of the product. The driving force is you'd rather have anti-coplanar. How do I know that's the driving force? Because if you go do this reaction in lab, guess which one you will get? That one. So we must then assume that the driving force is the anti-coplanar requirement. Let's do another one. I see a carbon with a leaving group. I see a strong base, anion. It looks sterically hindered. Got lots of big wings on it. It's going to keep it from getting into tight places. Sterically hindered base. What mechanism we're doing here? Is this substitution or elimination? Substitution or elimination? Joy?
Elimination.
Why do you say elimination? Because we're doing elimination right now? When you get to final exam, you're not going to have that, you're going to be open to anything. Why is this elimination? Why could it be substitution? If it was substitution, would it be SN1 or SN2?
SN2.
Be SN2 because we got a strong nucleophile. Can you do SN2 on a secondary halide?
Yes.
Yes. It's either SN2 or E2. Somebody tell me which one's going to be favored and give me a reason why.
E2.
Why is E2 favored?
Since it's sterically hindered.
What's sterically hindered?
The strong base is sterically hindered.
Sterically hindered. You remember when we did SN2, what really affects SN2? Sterics. Very sterically hindered nucleophile slash base. Also, this is secondary, which is a little bit sterically hindered. Primary would be less sterically hindered. You could theoretically do some SN2 here, but here's a take home. If you want to do elimination here, would you rather use this base or this base? Which base is better if you want this to eliminate?
The new H.
Well, which is more likely to do SN2, the thing you don't want? That's more likely to do SN2. There's no sterics. So if you want this to only eliminate, which base do you want to use? Over there. Should we pull out the substitution handout? Not sure that I have a substitution. Somebody have a substitution handout where we were talking about strength of nucleophiles? I don't see a substitution handout. Strength of nucleophiles? Well, I don't see it real quickly, but somewhere in there I tell you that sterically hindered bases are better for E2 elimination. If you wanted to eliminate, use a base that doesn't want to do substitution, right? Doesn't that make sense? Yes. While you theoretically could do SN2 here, this is more prone to do elimination. Sterically hindered bases are used for elimination. Now up here we couldn't do substitution because it was tertiary. You can theoretically do substitution here. Let's do an elimination. Show the elimination product. Are we doing E1 or E2?
E2.
E2, strong base. Show the E2 product. THF is just a solvent, tetrahydrofuran. Somebody tell me this real quick. How many theoretical beta elimination products are possible for this reaction? And when I mean theoretical, I really mean considering no theory. Because if you start considering theory, you'll say, well, there's only one possible. I mean, how many beta elimination products could you show here? Let's do that first. We did it up there, right? You have a beta hydrogen here. We'll call that A. There's actually two of those. But you also have a beta hydrogen here. We'll call that B. If we eliminate HCl with the H of HCl being A, what will the product be? If we eliminate that H and Cl, would we get this product? But this also has stereoisomer. That would be trans, but we also get cis as possible. We could also show a cis. What would be if we eliminated HB? We would have double bond there, and ethyl here, like that. Please note that this carbon is planar, and don't draw that as dashed or bold. But this could also have stereoisomer. Now this one we don't want to use cis and trans. It's got three things. Major groups are trans, so what is this? E? This is E? Yes. You would also get Z. There's 4 theoretical alkenes that can be shown. The 4 are on the board. From beta elimination. Does anybody see another one? I don't think I see another beta elimination product. Which one of the 4 is going to be formed? Tell me this. Next consideration. Would you rather form, if nothing else mattered, would you rather form this one on the left or that one on the right? One on the right. Why? More substituted. Okay, but eliminating the more substituted eliminate HBCl. If we eliminate HCl with HB, HB is more sterically hindered H, right? It's buried in here. What type of H is this? Primary, secondary, tertiary, what?
Tertiary.
It's a tertiary CH. It's on a tertiary carbon. What is this? It's a secondary CH. Tertiary CH is more buried in there amongst all those carbons. To get that product, which you said is the one you want, we're saying, hey, very sterically hindered base, I want you to abstract the buried H instead of the one that's more accessible. So that's what we want to ask it to do. The question then becomes, can it? Well, this is where it kind of gets vague. And there's no good answer for that. But I can ask you this question. If we wanted it to abstract this one, and this was too sterically hindered, does it make sense that we might instead use a less sterically hindered base, like maybe sodium hydroxide? Then maybe it would do that. The problem is, if you go to sodium hydroxide, yes, it's more prone to taking that H, but what is it also more prone to doing? It starts being more prone to doing substitution. In the end, a lot of these reactions have kind of two outcomes, and we can't give a take-home message. You have to know trends, though. The more sterically hindered this becomes, the more it's going to be prone to taking that H. But guess what? That was spelled out 2 pages ago, right? That was spelled out 2 pages ago. So I have to give you some information. I can't just say, show me the product. I might ask you this. Show me the Zaitsev product for this reaction. What's your answer? Well, first off, what's the Zaitsev product? Thermodynamic, more substituent. Right there, I'm telling you which one are we doing. There you go. I just told you, I want this one. But which one are you going to show? E or Z? What do you have to know then? Do you automatically get the more stable one? E? No, you have a stereochemical requirement when you're doing an E2. So, we're eliminating, if we're doing Zaitsev, we're eliminating HB. You've got to do this in a Newman projection, just like we did before. Do it in a Newman. Make sure HB and the Cl are anticoplanar, and see which one you get. Somebody got it? E or Z? Let's do it. I'm going to look down this way. You may have looked the other way. I'll look down here, down this bond here. Let's see, I'm going to draw it right here in the middle. Front carbon. Front carbon. What's coming straight down? Nothing. What's going out towards you on my right? Hydrogen. What's going to the hull off the first carbon? Alpha, yeah? Look past the first carbon on the back carbon. Back carbon is something going straight down in the plane of the board. Ethyl, so it's eclipsed with a methyl. What's on the second carbon going out towards you? Chlorine. Again, the HCl, they're planar, they're really eclipsed, but they're centoplanar in this original confirmation drawn here. What is on the second carbon going to the Hall? Hydrogen, and the Hall is to my left as I'm looking down. As I'm looking down, the H is to my left. Don't confuse which H we're talking about. We're talking about the one on the front carbon. I'm going to label it as B. Don't confuse it with this H. This H and that leaving group need to be what? Anticoplanar. I'm going to rotate, I reckon, the back and move the chlorine over here. Front, we still have HB here. Methyl here. Ethyl here. I'll rotate the chlorine here. Everything we're rotating 180 degrees. What is here? Back. That should be H. And what is straight up? Ethyl was straight down on the back. Now it's straight up on the back. We eliminate HCl through this plane. And what do you see? The two ethyls are on the same side of the plane. On the other side of the plane is a methyl and an H. Which product do we get? Two ethyls are on the same side of the plane. H and methyl here. So again, in this example, we're getting not the most stable isomer. E would be most stable. Ethyls opposite each other. We actually get Z. The Zaitsev product is Z. That would also be considered a Zaitsev product, but it's not the preferred one. Questions about that? What if this had asked you to show the Hoffman product? Which one would you have shown? It would have been the less substituted alkene.
You would have to choose between trans or cis.
Would it be cis or trans? I'm going to draw this back. Here's a take-home. You only have to do the Newman when there's only one beta hydrogen. There's only one beta hydrogen. It has to be anticoplanar to the leaving group. If you make the Hoffman, how many beta hydrogens do we have to deal with? 2. If there's 2 beta hydrogens, you do not have to do the Newman. Why? Because you really have a choice. You can eliminate 2 different ways. I would have to do this process twice. And if I do it twice, you're going to get either answer. But then you're going to have to use something to decide beyond that. And what do you want to use to decide beyond that? Thermodynamics. So if either one can occur, which is going to be favored? Trans. This would be the Hoffman product. If you've got 2 H's, forget about it. Show the best one. That means you have a choice. Over here we did not have a choice. There was only one H. That H has to be the one that's anticoplanar. When it's anticoplanar, the ethyls on the same side, this has to be the answer. Questions? There's some of these in the workbook. Nada.
If we right away do not get the new production as anticoplanar, do we have to still keep going to make sure that they are anticoplanar?
I can't hear you.
If we drew this and it already came out to be anticoplanar, do we just keep it as it is?
You wouldn't have to rotate it,
Okay.
right?
But still, if it's not, we do have to rotate.
Yeah. I mean, if you draw it and it's already anticoplanar, then you don't have to rotate it. Yeah. Good to go. Let's look at some examples with rings. We introduced this up there. The leaving group and the beta hydrogen must be anticoplanar. For this to happen, the leaving group has to be what? Equatorial or axial? Wednesday was a long time ago. The leaving group has to be axial. I should have brought a model. If you look at a group that's equatorial, the beta hydrogens are not anticoplanar. But if you make the leaving group axial, then you will have H's beta hydrogens that are anticoplanar. The leaving group must be axial. Now, is axial the best position for the leaving for a big group to be in? Usually, leaving groups are kind of big, like an iodine or a bromine. No. The leaving group actually has to be in the less preferred position, right? So, what's the product here? Some of these considerations are easier than the others. Let's start with this. How many possible beta elimination products can we show on the board for this compound? First off, is this elimination? That's a secondary halide. It can do a substitution. What is TEA? Triethylamine. It's nitrogen with 3 ethyls. Triethylamine. It's a common base. Is this weak or strong? It's not an anion, but it is an sp3 nitrogen. This is a strong base. Now, it's not that strong, but for what we said, that is a strong base. It's strong enough to do a bimolecular reaction. It's a common base for doing eliminations. Because it doesn't like to do substitutions. Why not? Why is this not good for substitution? Sterically hindered. It's a common base for doing E2 elimination. Now that we know we're doing E2 elimination, show how many possible beta elimination products are there? Just all possible. How many are there? Somebody say it.
2 beta hydrogens and 4 products.
Why 4 products? I see a beta hydrogen here, HA, and I see beta hydrogen here. There's actually 2 there, but either one, would it give the same product? Did you get a different product depending on if you eliminated these?
Those you get sister trans as well.
I don't see any cis or trans possible. If we eliminated HA, we would get that. If we eliminate HB, what do we get? When we get that, let's see what we're doing. We just remove the H in the leaving group, put in the double bond between them. Do either of these have isomers? This cannot have a cis-trans isomer, not with a ring. It would be impossible for this to go that way and be connected. Neither of these have isomers here. These alkenes are not stereogenic. Only 2 possible beta elimination products. Which one's going to be formed? Let's label them as Satzev for Hoffman. Which one's Satzev? And this one's Hoffman. More substituted, less substituted. Which one would you like to make? Or who cares about you? Which one would nature like to make based on thermodynamic rules? Thermodynamically, this is the favorite one. Somebody suggest a product here. We got a sterically hindered base. Really, this gets us into the conundrum. Is this so sterically hindered that it can't abstract HA? It's hard to know. We know that the more sterically hindered this becomes, the more it is going to abstract these because they're in a secondary carbon. But, hold on, we do have a stereochemical requirement. Can it abstract this H here if we consider the stereochemical requirement? Is this H anti-coplanar to that leading group? Keep in mind, anti is synonymous most of the time with transcoplanar. Is that H transcoplanar to that iodine? It is not. It's not even trans. This H is cis to that iodine. Now I can draw you the chair conformation and show you. In fact, let's do that real quick. Boom, 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 boom. If we put the iodine here, I put it straight up. Why am I putting it straight up? Because the leaving group has to be axial, because only with its axial will it be anticoplanar to the H, right? Adjacent here. The next carbon, I'm going to come next carbon down. Got an ethyl. Is this ethyl axial or equatorial? Well, the ethyl is trans to the iodine. So if the iodine is this axial or equatorial? Equatorial. No, it's axial. Trans, right? Aren't these trans? That's bold, that's dashed. Remember this? Trans. Where's the H here? There's the H. It's above the H. It's below the H. They're trans. HA. Here's HA. There's the leaving group. Is HA and the leaving group anticoplanar? Leaving group is straight up. This needs to be here to be anticoplanar. Straight down. Look at the very top. You see this? Br straight up, H straight down. We have a scenario where we got the leaving group here and the H here. See, I told you the take-home. Transcoplanar, but they're not even trans. The leaving group and the H are cis. Where are we at? Right there. Here's the take-home. This H here, forget about it. You can't eliminate that H because it will never be anticoplanar to that leaving group. You do not have any free rotation here because of the ring, so we can't rotate it like we did with the others. This cannot form. It cannot meet the stereochemical requirement. Which one are we going to get here? Because let's draw these two H's in on this over here. We draw them in. Let's see. This is a down carbon, so it gets a down, and it gets one like this. It's supposed to be equatorial. Right? Which one is straight down? A or can I call this C instead? So make them different. Which one is straight down? B or C? There's an H here, there's an H here. Which one is B, which one's C? Well, the iodine's up. Straight down is trans. Which one's trans?
C.
C. And that's B. So when it eliminates, which one actually gets eliminated? Which one is anticoplanar to the iodine? C. That's the one that gets eliminated. So if these were designated with a B or C, which H would remain? HB remains. HC is the only H of the three that is anticoplanar to the leaving group. But isn't that what we were looking for? Didn't we start off by saying the H has to be anticoplanar to the leaving group? So doesn't it make sense to find which one is? That's all we did there. This reaction gives the Hoffman product, because it can't give the same set because the H will never be anticoplanar. I want you to do this on your own here. Because, another consideration. If you notice, the conformation I drew here is not the best conformation. I've got the two big groups axial. That's not the best conformation, is it? But if this moves to the better conformation, and this goes equatorial, can it eliminate from that conformation? It cannot. The more it exists in the conformation with the leaving group equatorial, the slower the reaction will be. Which reaction would be faster? The one where the iodine is more likely to be axial. That's the one that will be faster. The one with the iodine more likely to be axial. So based on that, figure out which one would more likely be axial. Maybe neither one will be axial all the time, but which one is more likely to be? Maybe 20% as opposed to 10%. Okay, let's move on. Any questions about that page before we move on? At this point, we got some miscellaneous things to add in. Touch miscellaneous here. Still very important. When either substitution or elimination is possible, which will occur? I sort of alluded to this. Sometimes you can have both. Here's some important things to consider or remember. Heat favors elimination. Why? Because entropy. Because when you eliminate, you're essentially converting one molecule into two. If you have this molecule, maybe you eliminate HBr, and you have a new molecule plus HBr, two molecules. So entropy is being favored. And if you look at your Gibbs free energy equation, which term does heat amplify? We've said this before. Delta G equals what? Delta H minus T delta S. Temperature magnifies entropy. And so if entropy is good, how do you make it even better? Heat. You'll magnify it. Elimination, entropy is good. If you heat, you'll make it even better. Heat favors elimination. In this example here, I just kind of illustrate this. If you take this plus water and heat it, we can show an elimination product plus HBr. Really, water just was a spectator. Okay? It really just didn't really do anything here. It might have acted as a base, but you could have Br act as a base. One molecule going to two. Entropically favored. Thus, if you heat, you'll make it even more favored, because heat amplifies entropy. On the other hand, if we do a substitution, if this reacts with water to give this alcohol plus HBr, there's no favorable entropy here. 2 going to 2. So, I mean, Will heating improve this reaction? No. If you multiply 0 by 100, it's still 0. Right? What's the take-home message? It's in bold. Heat favors elimination. Mark?
Why water is spectator the first one and not the second?
Well, did water do anything in the first one? I mean, overall in the equation? No, it's on both sides. It didn't do anything. But water did something here. It's now bonded here. I mean, it's just a spectator up there in terms of the equation. It may have played a role as being a solvent and promoting ionization, but it didn't undergo any change at the end. Another take-home message. Involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. So you have to know how to judge nucleophilic strength. What's the better nucleophile of the halogens? Iodine or F minus? I minus or F minus? I minus. I minus is a good nucleophile. Thus, if you have I minus, it'll tend to want to do substitution. That's what I'm saying here. Good nucleophiles tend to want to do substitution. And I can give you theory why, but just take home message right here. On the other hand, F minus is a lousy nucleophile comparatively. F minus doesn't like to do substitution. Actually, that's a problem in organic chemistry that's trying to be solved. How to get F minus to be a better nucleophile. Instead of doing substitution, F minus prefers to do what? It prefers to act as a base and do elimination. That's what we're saying here. For example, you take this alcohol with HBr, you can get a substitution. This is just like we did in lab, shaken not stirred, except we used HCl instead of HBr. So you got substitution. But if you take this same alcohol and react it with HF, you're going to get the alkene by an E1 mechanism. And I'll walk you through the mechanism. You protonate this with the acid, that is an acid. Water ionizes off to give this cation. And then the F minus, instead of adding to the cation and giving you an analogous substitution product, instead it acts as a base. And how do you get the final product? It acts as a base and takes an H, moves this in, creates HF. That was an E1, right? You see the difference? The better nucleophile will add as a nucleophile. The worse nucleophile will act as a base. That's a general trend. And I explained that there. We're reading from there. This, H plus, HSO4 minus. Have we ever used HSO4 minus as a nucleophile in this class? No. Bad nucleophile. This is just a source of H plus. Because it's a bad nucleophile, we can just protonate ionize and make this carbocation. It will not add to the cation. It's a bad nucleophile. Instead, something will just take an H. Maybe this, maybe just water. Put the electrons in, and you get the double bond. This is a common reaction of alcohols. To dehydrate them, we remove water. This now has loss of H2O. Dehydrate with this. You would never do this reaction with HBr. HBr is a good nucleophile. HBr will give you a substitution product looks like that. Or it could rearrange. You might get a rearrangement, the VR ends up there. And I keep showing you things that are on the paper already. Okay, let's at least look ahead at these. There's a few more miscellaneous points. Okay? Very important. One of them is the silver ion, which we used in lab last week. We also have some more kinetics, types of solvents that are good, and some information about solvents. And then at the end there, we show double E2 elimination, which you did yesterday in lab and which we're doing today in lab. If you double eliminate, you don't get an alkene, you get a alkyne. If you double eliminate between the same two carbons. And we'll finish this up on Monday. We need to have a quiz on Monday. Quiz over substitution and elimination. Okay? And then Monday we'll finish this up, and then that's it for next week, right? We're off. I think that's it, guys. Remember the seminar today at 1 o'clock? Get there early. Be standing room only. It's going to be a good one. We'll give you the entire seat, but you're only going to need the edge. That's Dr. Hager right there.